Hi, Mr. Sapone here, and today we're going to look at electronegativity and bond type based on electronegativity, and we're going to talk a little bit about determining whether molecules are polar or nonpolar. I'm going to start with the question, what type of bond will aluminum and chlorine form? We know this as aluminum chloride. Aluminum has a +3 charge usually, and the chloride anion is a -1, so you need 3 chlorides to combine to form aluminum. And you might be thinking, well, this is going to be an ionic bond because we have a metal and a non-metal joining together. And that would be a great guess, but in this case, we're going to be better off calling this a covalent bond, and we're going to see why. In general, metals and non-metals form ionic bonds, but we're going to get a little deeper in talking about bonds and how to determine bond type in this screencast. And to muddy waters a little bit more, technically, there's really no such thing as an ionic bond, a purely ionic bond. We'll talk about what that means towards the end of this screencast, but don't let it confuse you for now, but we'll get there. So electronegativity, recall that electronegativity is basically an atom or group of atoms' tendency to attract electrons. How badly does sodium want to attract another electron? And if we recall, sodium is going to actually want to lose an electron. It's not going to have a very high electronegativity. And we'll talk about trends. As we go down, we saw when we covered the periodic table, electronegativity, the attractiveness or the pull for additional electrons decreases. Because as you go down, there's more energy levels, and you're getting further away from the nucleus. Per Coulomb's law, if you double the distance, the force, the pull of the nucleus goes down by 4 times as much. And if you triple the distance, it goes down by 9 times as much. That was our inverse square law. So these are not exact pictures of an atom. They exist in those orbital shapes, SPDF, and those weird, funny-looking regions. But generally, the higher energy level, the further away you are. So there's not going to be a lot of attraction based on Coulomb's law. And the other thing is there's electron shielding. In order to pull another electron here, sure, this nucleus is pulling electrons in, but these other electrons that are going to be between the additional electron and nucleus are shielding it. They're repulsing it because like charges repel. So these electrons are going to say, hey, we don't want you here. So as you get more shells, there's more electrons between it and the nucleus. There's more electron shielding, which makes it harder to pick up a nucleus, an additional electron. So electronegativity increases going down. As we go across the periodic table, electronegativity increases because we're adding electrons to the same energy level. We're not getting any additional shielding or additional energy rings. So just recall there's some trends in electronegativity that we talked about, little review. And electronegativity really deals with an electron tug of war. We know that 2 hydrogens will bond together as a diatomic molecule. And you basically just have an H. And H bonded together, and they're sharing an electron pair. This is a hydrogen-hydrogen bond. They're sharing their pair of electrons. Now, hydrogen has an electronegativity of 2.20. And we can think of these numbers, these electronegativity numbers, as how strong they're pulling on the electrons. Each one of these hydrogen atoms is pulling on this shared electron with 2.20. And essentially, they're pulling this with the same force on those electrons. So they're going to share them equally. When we have hydrogen fluoride or hydrofluoric acid, if it's aqueous, it's going to be a little different. We have a hydrogen and a bond to fluorine. Hydrogen is pulling the electrons with 2.20, right there. But fluorine is pulling with 3.98. It's pulling the electrons closer to it. So in essence, these 2 electrons that they're sharing for the bond, they're actually going to be a little bit closer to fluorine. They're going to spend more time around the fluoride anion, the fluorine end of this molecule, than they are the hydrogen end. And that's going to make this side slightly negative. Why? Because the electrons are spending more time over here, less time around the hydrogen, so the hydrogen end is going to be slightly positive. So we end up with a polar molecule. And that's a little messy, but the exact same thing happens with water. In H2O, we know we have an oxygen connected to 2 hydrogens, And the hydrogens are pulling with 2.20, right? Each hydrogen. And we treat the cases differently. This is pulling down with 2.20. The oxygen is pulling up with 3.44. So these two shared electrons, they're actually going to be a little closer to the oxygen end. And the same exact thing happens over here. They're a little closer. So what we end up with is this side of a water molecule is negative, and this side down here is slightly positive. So the polarity of water is actually due to electronegativity and this sort of electron tug-of-war. So when we have covalent bonds and electrons are being shared, we sort of have a tug-of-war going on. And that's why water is a polar molecule, because the electronegativity of hydrogen and oxygen is different. Oxygen pulls the electrons a little bit stronger than hydrogen, resulting in a polar molecule. So this explains our drops on a penny lab, why we were able to fit so many drops of water on a penny. If you put 2 drops of water on a piece of paper, or like wax paper next to each other, they'll snap together. We saw a lot of experiments with surface tension where we turned jars upside down with a little film over them and the water didn't come out. Why you can build a snowman but not a sandman. It's the water in the snow, or a mud man you can build a sandcastle with mud. It's got to be a little damp. The water inside is going to hold things together. Capillary reaction. Melting point, boiling point, solubility, all of these things are explained based on water's polarity, which in turn is related to electronegativity differences, which can be explained in terms of Coulomb's law, nuclear charge, electron shielding, and things of that nature. So it's a very detailed explanation of what's going on. And when we are determining bond type, we determine bond type based on the difference of the electronegativity values. So aluminum and chloride, we're going to start with this one down here, and we're going to see how to do this. So this scale right here, this table is the same as this table down here, and we just have our electronegativity values here. And the idea is when you basically got to compare the electronegativity of aluminum to chlorine and to see which one is pulling the electrons more. And you get the difference between them. Aluminum is a 1.61. And chlorine is a 3.16. So always subtract the bigger number minus the smaller. That's going to be close to, I think, around 1.6-ish. It's not quite there. But the idea is you just get the difference between the two numbers, 3.16 minus 1.61, and you just match it up to where it is on the table. And I know that this answer is going to be between 1 to 2. So we're going to call that a very polar covalent bond. And the idea is right here, if electrons are shared equally, then the difference is 0. Like hydrogen is 2.20, and H2 molecule, we'd have 2.20 minus 2.20 is 0. That means the electrons are shared perfectly even. When the difference between electronegativity gets bigger, when it gets really great, we start calling it ionic. When it gets above 2.0, we would call that an ionic bond. And table salt we know is an ionic bond. So let's look at that one. Na is 0.93. And Cl is 3.16. We don't even need the numbers. I know that when I subtract 3.16 minus 0.93, the value is going to be greater than 2, which means we call this an ionic bond. But even in an ionic bond, there's going to be a degree of sharing. But we say the sharing is so strongly towards the chlorine or the chloride side that the electrons are going to spend most of their time there, so we're just going to say they're transferred. It's not 100% true, but we are going to still use the nomenclature ionic bonds. But this is really what's happening. It's sort of a scale. The electronegativity difference determines to what degree the electrons are shared. Are they shared equally, or are they going more towards one of the atoms in the bond? And carbon dioxide, again, don't worry about there being 2. We would treat it separately. Carbon dioxide would be COO, and actually this would be a double bond. But carbon has an electronegativity of 2.55, and oxygen 3.44. And I know when I subtract these, 3.44, and you do it for each side, you don't have to worry about there being 2 oxygen, you just treat each case separately. 3.44 minus 2.55 is going to be less than 1. It's going to be somewhere close to 1, but less than it. So we're going to call this a polar covalent bond. So carbon and oxygen is a covalent bond, two non-metals. They always form covalent bonds. Slightly polar, but we're going to talk about in a minute whether this molecule, is this molecule polar compared to water? And I don't believe it's going to be, so we'll see why in a second. So to determine the bond type, all you do is get the electronegativity difference, match it up with the chart. Pretty straightforward. Carbon dioxide is actually going to be nonpolar, and we're going to look at why. Well, oxygen is 3.44, and both of them are 3.44. And carbon is 2.55. And when you do get an exact difference, it's 0.89, and that falls in the 0.5 to 1 range. So it should be polar covalent. And it is a polar covalent bond. What this means is these electrons are going to be a little closer to the oxygen end than the carbon end. So this end is going to be slightly negative, slightly positive. This isn't polar because opposite ends of the molecule have the same charge. That's kind of the definition of polar we're working with. Opposite ends got to be opposite charge. One side's got to be plus, one side's got to be minus. And it just so happens that they are both positive. So because carbon dioxide is linear, whereas in the case of water, water is actually bent. So we have to take into consideration the shapes of molecules, minus, plus. So one end of this molecule is negative, one end is positive. But if water was shaped like carbon dioxide, if water was shaped like this, water would also not be polar. But because water has a bent shape, this would be the hydrogen, there'd be a plus and a minus, and it would cancel out. Because water is bent, it is polar. Because carbon dioxide is not bent, there's a negative on each side, it is non-polar. And we draw those, and this is just delta, I believe a lowercase delta. It just means a partial negative, slightly negative, because the electrons are closer. So these are polar covalent bonds, but this is not a polar molecule because it has a linear shape and opposite ends have the same charge. You would need a plus side over here and a minus over here, or a plus here and a minus here to make it a polar molecule. And water, we said, was bent, so water has polarity. If water was linear, it would not be polar. It would be in the same case as carbon dioxide. And we'll just look at HCN, same thing. Hydrogen is a 2.20. Carbon is a 2.55. And nitrogen is a 3.04. And this, when you subtract these, it's going to be really close to 0.5. So it's going to be just slightly polar. And either way, you see this is pulling, so the electrons are going to be a little closer to nitrogen than they are to carbon, just because the electronegativity is different. There's going to be a net, we call it a net dipole. The electrons are going that way, right? Put a line through there. And in this case, carbon is actually pulling on these two electrons a little bit more than hydrogen is. So there's also going to be another net dipole moment that way. In essence, even though it's very, very slight, this side's going to be slightly positive. This side's going to be slightly negative. So this is a polar molecule, despite the fact that this bond is certainly nonpolar. And this bond is either nonpolar or it just, depending, it's 3.04 to 2.55, like just hits the 0.5. So it's either just polar or it's right on the borderline. So even though this molecule is not really very polar covalent bond, doesn't have polar covalent bonds really, we have a polar molecule because there is a net dipole moment. The electrons are going in this direction, so this side becomes negative, this side becomes positive. So the idea is polar covalent bonds, electrons are shared unequally due to electronegativity differences right here, and nonpolar, they are shared equally. And we talked about carbon dioxide versus water. It's a good case study. Carbon dioxide has polar bonds, but it's not a polar molecule because it's linear, cancels, whereas water is a bent molecule, so it is polar. That's electronegativity. Mr. Spohn.